And now I would like to start the session on smart production machines and processes. And I would like to follow the presentation of Martin Massage, and I wanted to say that we as mechanical engineers are strongly focused on the quality, but we are not aware of that because we know physics, and we use the physics for modeling of our processes. And the first presentation will be done by Dr. Matěj Sulitka. He is head of Research Center of Manufacturing Technology, and he will present digital twin of machine tool for predictive optimization of machining operation.
So, thank you for the introduction. It's my pleasure to give you some picture about the use of digital twins for prediction of machining operations and results of machining. I will try to keep the presentation short to stay within the time borders. So I will go to the content of the presentation. Actually, why do we need to cope with digital twins for machining prediction is quite clear from the complexity of machining operations, which start from the NC code generation, and the whole chain goes through different stages of CNC control, feed drive control, machine tool structure, and the process itself, which generates at the end of the whole chain the final product, which can fulfill the requirements on accuracy, productivity, quality of surfaces or not. And this is the issue since there might happen many troubles which need to be addressed and solved. Actually, what can we do for having the process stable and robust? Of course, at the first stage, we need to set the cutting tools, cutting strategy, cutting parameters. We need to adjust post-processor. We need to adjust parameters in the machine tool control, CNC control, feed drives. We need to adjust setting of the workpiece in the machine tool working space, taking into consideration the dynamics of machine tool and workpiece in some specific cases. And last but not least is then the issue of machine and workpiece interaction. The processes, as they are commonly prepared nowadays, lack the information on what is the dynamics of the machine tool behavior, and this brings many troubles in terms of not knowing exactly what will be the result of a machining operation. This needs to run on many iterative steps before the final product, fulfilling all the criteria, is achieved through the measurement, adjustment of NC code and machine tool setting. We can use digital twins. We can have different types of digital twins. I will talk later about the digital twin, which we call process digital twin, and its application for predictive purpose of predicting the machining operation and its optimization. Generally, there are digital twins for many applications which serve for testing the PLC and CNC setting of the machine, which just use the kinematical model of machine tool structure. Those are the models which we call models for virtual commissioning. The other side of the slide shows the concept of digital twin and its integration with the data from the processes, as will be handled later by next speaker. We have the digital twin, which is a realistic representation of the physical system of a machine tool, its structure, dynamic behavior, control. And this allows then the realistic simulation of machine, process, and workpiece interaction. By having that chain, we are capable of a detailed simulation and visualization of machining results. There might be different levels of digital twin according to the application. The basic one, which just takes into account the NC data, we may call it as chem level, which serves as a very preliminary check of machining operations. The next level is the CNC level, which integrates already the CNC controller, which brings quite many problems and possible errors which we may see on the final product. The next step is also the integration of machine tool dynamics, which further gains or eliminates the errors introduced by the CNC controller. And the highest level is the process level of digital twin, which integrates all the physics of the process, including cutting forces, deflection, static deflection of cutting tool, workpiece, issues of chatter, stability of the process, vibration, and this relates especially to the most complex machining of lightweight or thin-walled workpieces. That structure of digital twin allows a detailed insight into possible sources of errors in machining operations, and thus allowing understanding better what's happening in the process where we need to search for sources of errors. Here on the picture we can see a visualization of different errors coming from either the CNC interpolator or the full machine digital twin. Everything can be integrated in machine tool and process simulation, which delivers all possible data, allowing better understanding of the process and better understanding from where the errors are coming and where should we optimize the process. Here we can see various parameters and variables which are helping us in understanding the processes, starting from the NC code quality and distribution of NC codes, tool engagement, cutting forces, tool load, spindle torque, and finally we can check what all this, everything with the integration of CNC control, feed drive control and machine tool structure brings on the final result of machining operation, checking the accuracy and quality of machined surfaces. A few examples here are the applications showing the use of process digital twin for optimizing the processes, where we either can optimize the machine tool parameters or process parameters. The first example here is mold machining, where we try to get possibly highest productivity of the process and at the same time to keep the accuracy and quality of the machine surface within the defined borders. Here, that real example from practice showed that by the digital twin we identified possible boundaries in increasing the productivity of the process by optimized setting of the CNC controller, which brought increased productivity by almost 20%, and at the same time increased surface quality, where the optimized setting of parameters eliminated the errors on the surface quality. Higher level of the digital twin application and optimization of the process are the processes where we machine thin-walled flexible workpieces, where we struggle mainly for chatter-free cutting conditions, low deflection of the workpiece, and last but not least, also the complexity of 5-axis machining. Here the example shows machining of steam turbine blade and its optimization, where the first result of machining, as it has been prepared by conventional approach, brought many errors on the surface, mainly quality issues. And by using the digital twin, we can we could test many different strategies without any need of running physical tests on the machine, thus saving time and costs. Which showed here a very effective application of spindle speed control and finding the cutting conditions which avoided the elevated vibration of the blade, and at the same time, again, you can see a significant reduction of machining time. This brings the challenge, or this brings the challenge to integrate both the static and dynamic behavior of the workpiece into the machining simulation, into the digital twin, which can allow integrated optimization for both minimizing the static deflection and increasing the dynamics of the process and elimination of vibration issues during machining. In the simulation software which we are developing at RCMT, we can run the simulation integrating the dynamic behavior of the flexible workpiece depending on the material removal, and to predict both the static deflection of the workpiece and stability limits of processes, which on the example which I'm showing here brought again a positive result in eliminated quality issues on the surface by setting different machining strategy and cutting conditions. So this brings me to the end of this short overview of the applications of digital twin technique for predictive purposes, where, as I can summarize by already quite a number of practical applications, we may confirm that the digital twin is capable of running relevant simulations, delivering relevant results, and offering then the opportunity for optimizing the processes with respect to the parameters which are set as the requirement on the of the workpiece. Thank you for the attention. So I'm ready for answering possible questions later.
Thank you.